Hello, my name is Avtandil Giorgadze. You may call me Gio. I'm a solutions engineer here at Fortress Power. And today I want to talk to you about the eWays, eForce batteries, and Envy True12 inverters. We will discuss 4 different cases of 4 different configurations, which can be achieved without having any external bus bars, by only using the built-in internal bus bars inside the eWays and inside the Envy inverters. Then we'll also get creative, and we're going to talk about the unshared battery bank, and we'll talk about the age-old method of using external bus bars with the batteries to join the batteries together, creating one single battery bank for one inverter or multiple inverters to charge or discharge. So before we start, I need to make a couple of notes. So in all 4 cases, remember 4 cases being the ones in which the external bus bars are not used, even though you might have multiple inverter quantity, multiple battery quantity, external bus bars are not used. And that creates the 4 different configurations, and those are our 4 cases to discuss today. So in all 4 cases, battery-to-battery communication is established. That is a requirement that you must have closed-loop communication between the batteries and the inverters. If there is a circumstance in which that cannot be achieved and you need open-loop communication, that must only happen with tech support's approval and assistance. Only eWay 1 receives an optional guardian. So if you have a group of eWays or group of eForce stacks, each one obviously having its own eWay on the top, only first stack or first eWay will receive the optional guardian unit. Again, guardian is optional. That doesn't mean that you have to have it. Only eWay 1 communicates to inverter. So the idea is that even if you have multiple eWays, i.e. multiple eForce stacks, the eWays communicate to each other, and the primary eWay number 1, collects all the data and communicates that data to the inverter. No external battery bus bars are used. As I said, these are 4 cases specifically which are 4 configurations with no external bus bars, although there are multiple batteries and multiple inverters. The inverters use a single shared battery bank. Yes, we're not grouping the batteries per inverter. We are creating one shared battery bank. Only these 4 configurations are allowed without an external bus bar while having a shared battery bank with the inverters. So in one of the solutions, you will see that you essentially daisy chain 2 batteries, and that is a great modularity that we offer, but one might think, oh, if it works for 2 batteries with the same logic, it can work with 3, 4, 5, or 6 battery stacks. That is not true. It cannot work. It's not that straightforward and linear. So only these 4 configurations are allowed if you have no use of external bus bars, or if you're not grouping the batteries per inverter. So these 4 cases are with no external bus bars, but with a shared battery bank. So once there's a voltage from the batteries, all of the batteries and all of the inverters will see that voltage, right? Then this is this text in red. This refers to all cases, not only these 4, but all cases in general. So in all cases, the multiple inverters communicate to each other or with each other, and their applicable AC ports are combined in a combiner/splitter panel. So what this says really is that the inverter to inverter communication is mandatory. You must have it. When inverters communicate with each other, they must support the same load panel or the same group of load panels. That is also a requirement. And that's why we see combiner panel here. Splitter panels comes into play when you have external AC source. Let's say you have grid and you have 2 inverters. That grid connection should be established between the grid and inverter 1 and grid and inverter 2. So that's why you need a splitter panel, so you can essentially, quote unquote, split the grid into the signal to two inverters. And same applies to the generator port if you're using AC coupled PV or you're using a generator. This is as just a side note, just for clarity. So with that, let's remember what we have inside the inverter and what we have inside the Envy. Let's start with the inverter because there's only one aspect that I want to cover. You have battery ports, 2 positives and 2 negatives. So port 1, which is now occupied, positive port 1, vacant in this case, positive port 2, occupied negative port 1, and vacant negative 2. Then inside the eWay we have positive bus bar 750 amps, negative bus bar which is also 750 amps. By default you have one of the ports on this bus bar occupied by the positive and negative connections. So right here you see positive and you see negative. So with these connections in place, which are default and always there, you have 3 vacant ports available. Let me use a laser pointer. So positive to the eForce units in the stack, negative to the eForce units in the stack. So that leaves you with 1, 2, and 3 vacant, and 1, 2, and 3 vacant ports on each bus bar. In this case, 2, these 2, because this picture shows the inverter already connected to the eWay. So that's your positive and that's your negative. And you see the optional guardian. As I said, only in the group of batteries, only one guardian is needed, and that lives inside the primary or first eForce unit. So with that, let's discuss the cases. Case 1, 2 eForce batteries and 1 Envy True12 inverter, and this can be achieved via 2 methods. We're going to start with method 1, paralleling the batteries at the inverter. Okay, very straightforward. This is by far the easiest one that we're going to discuss today. We remember there are 2 positive ports and 2 negative ports in the inverter for the batteries. So 1 positive port is occupied by eWay 1, 1 negative port is occupied by eWay 1 as well, and the second positive and second negative are occupied by eWay 2, and voila. So essentially right here your batteries are combined and the inverter sees the combined battery bank. Very good. So inverter positive, inverter negative, inverter positive, inverter negative in both of these eWays. Now let's switch to method 2, paralleling the batteries at an eWay. So previously we paralleled the batteries at the inverter. Now we're going to do the same thing, but we're not going to parallel them at the inverter, but at the eWay itself. We're going to use eWay 1 in this case. So 1 positive and 1 negative connects to eWay 1. So these bus bars automatically are connected to the inverters, or inverter. In this case, we only have 1 inverter. And this eWay 1 is connecting the eForces, the imaginary ones that are underneath it, to the inverter. But we have the bus bar to which the eWay 2 is connected. So because you have the connection between eWay 2 and eWay 1, these bus bars serve as the combiner bus bars. So this bus bar combines the eWay 1 positive, for example, combines the positive from eWay 2, i.e. all the positives of all the eForces that live under eWay 2, positive of the inverter, DC positive, right here, and positives of all the eForces underneath it. So this positive bus bar joins everything on the DC side, both on the inverter and the eWays. And same is the story with the eWay 1. So again, we parallel the batteries and we have battery 2 negative, we have battery 2 positive, we have inverter positive and inverter negative, which is great. So again, we avoided using an external bus bar, and this approach actually could be more useful in the field because you need less conduit length and you need less cable length, which saves you a couple of dollars and also a ton of time if you ask me. So next, we're going to switch to case 2, 3 eForce batteries and 1 Envy True12, paralleling 3 batteries at an eWay and the inverter. So here's what we're going to do. Just like before, we have eWay 1 and eWay 2, but we remember that we had the second positive and second negative vacant inside the inverter. So just like before, we have eWay 1 and eWay 2 joining each other inside the eWay 1 on the bus bars of the eWay 1, and then that connecting to the inverter, thus paralleling the inverter, eWay 1 and eWay 2. But because we have the second positive and second negative port, we're going to connect eWay 3 to the inverter. Now, interesting thing here is that the way the communication will work is that eWay 1 will communicate to, I'm sorry, let's start with eWay 3. eWay 3 will communicate to eWay 2, eWay 2 will communicate with the eWay 3, and eWay, what am I talking about? Sorry, long day, it's already 6:20 p.m. So today's stress took a toll on me, as we can see. So eWay 3 communicates to eWay 2, eWay 2 communicates to eWay 1, eWay 1 communicates to the inverter, and there's only one guardian inside eWay 1, as we discussed before. Another thing is that we have two sets of positives and two sets of negatives, one pair of positive and negative for group 1 and the second positive and negative pair for eWay 3. These cables, the ones going from eWay 1 to inverter 1, or one inverter in this case, or from eWay 3 to the inverter, those must be the same length, not to introduce drastic difference between the internal resistances, right? So please keep that in mind. This is very important. We also have a separate course on how important it is, and you're welcome to check it out. I think I called it Paralleling Batteries. I prepared it for NAPSAP 2025. I believe we're going to make it available on YouTube and our training portal very soon. Very soon compared to today. Today is April 21st, 2025. So again, battery 2 negative, battery 2 positive, right here. Inverter positive, inverter negative, again, right here. We have inverter positive again, but for eWay 3. Inverter positive and inverter negative, again, for eWay 3. So half of the 4 cases we have covered. Let's go to case 3, 4 eForce batteries and 1 Envy True12, paralleling 4 batteries at an eWay and the inverter. So this is very similar to what we saw a moment ago, but instead of eWay 3, you have a group of eWay 3 and eWay 4. So everything that I have said about the eWay 2 applies here as well. The only thing that I would like to add here is a note about communication. Previously it was 3, 2, 1. Here it's going to be 4. In eWay 4 will communicate with eWay 3. eWay 3 will communicate with eWay 2, and eWay 2 communicates with eWay 1, which on its own part communicates to the inverter. Again, here's what the connections look like. Battery 2 positive, battery 2 negative, inverter positive, inverter negative, an almost symmetrical situation, not almost, symmetrical situation with the second group. So everything else is identical. It's just the communication is a little different. It's 4, 3, 2, 1. So these groups don't independently communicate with the inverter. But in terms of power cables, the length for one group should be the same as the cable length for group 2. Group 2 being eWay 3 and eWay 4. So I'm not going to spend any more time on case 3. I think it's very clear. And let's go to case 4. 2 eForce batteries and 2 Envy True12s, paralleling 2 batteries and 2 inverters at an eWay. Now this is by far the most interesting one and the most complicated one, but I'm not saying that to discourage you. Complicated compared to the others, not complicated as such. So let's get into it. We have 2 inverters and 2 eWays, eWay 1, eWay 2, and inverter 1 and inverter 2, right? Before we start, I'm gonna verbally say what conceptually we are trying to achieve. So what we're trying to achieve is with the bus bars inside these eWays, we are trying to create one big bus bar. So here's what it looks like. You have positive cables, 2 of them, going from eWay 1 to eWay 2, and 2 negatives going from eWay 1 to eWay 2, right? So now whatever you connect to eWay 1 essentially connects to eWay 2 and vice versa, because now the connections are shared. You might be asking, oh, why the hell are we using 2 cables? What a waste of money. We could have gone away with 1 negative, 1 positive. I disagree, because 1 positive and 1 negative, how big of a cable would you use? 4-aught? Okay, fine. Well, what can it do? On the best day, 300 amps? Well, the inverters can output 500 amps. Those cables would melt. So that's why you're using a bigger cable, because you want to make sure that if something happens and eWay 1 disconnects and stops accepting power, yet the inverter 1 and inverter 2 are outputting maximum power, that these cables can withhold the hit. And Busbars have no problem with that, because the Busbars are rated at 750 amps. So that's why you have 2 pairs of cables, so that you have that ampacity that you need. And then all that is left to do, really, the eWay and eWay1 and eWay 2 are paralleled. The only thing remaining to do is to connect the inverters to these eWays. So eWay 1 and inverter 1, and eWay 2 and inverter 2. In terms of communication, nothing really changes much. eWay 2 will communicate to eWay 1, and eWay 1 will communicate to inverter 1. So now, let's talk about the other cases being these 2. Multiple Envy inverters and multiple Envy batteries, such that equal quantity of batteries can be connected to each Envy inverter. I know it's complicated when I read it, but the idea is very simple. So you have multiple Envy inverters, right? And each inverter will have its group of batteries. And because you have these 2 groups and 2 inverters, what you're trying to do is to make these groups symmetrical, and that's why you have the same quantity of batteries per group. That's going to be very easy to understand once we get to the slide that has the diagram or conceptual diagram of that, and I'm sure you're going to understand, but this is a brief introduction, so to speak. And then we're going to discuss use of external bus bars, and it's not given here, but I'm gonna give you a small bonus at the end. That's gonna be the solution that you derive from combining these 2 approaches together, right? So let's start with the easier case, not the bonus case, but unshared battery bank, just like we said before. So unshared battery bank. Multiple Envy inverters and multiple Envy batteries, such that equal quantity of batteries, again, equal quantity of batteries can be connected to each inverter. Simplest example being inverter 1 and inverter 2, eWay 1 and eWay 2. So these group, the word group itself implies plural, right? Multiple of something. Well, this is a group with only 1, eWay. But the idea is the same if you had 4 here and 4 here. Matter of fact, we can take a look here as well. So you have group of 2 eWays, and here the same, you have eWay 3 and eWay 4. What happens is that this group connects to inverter 1. So inverter 1 has its own small battery bank of 2 eForces, or stacks of eForces, one with its own eWay on the top, and you have inverter 2, again 2 stack of eForces, each with its own eWay, eWay 3 and eWay 4. What is extremely important here is that each group, if guardians are used, each group receives its own guardian, right? Because there is no communication between these groups as such. Matter of fact, eWay 2 communicates to eWay 1, and eWay 1 communicates to inverter 1, and eWay 3 communicates to eWay 4, and then the eWay 4 communicates to inverter 2. So there is no battery-to-battery communication between the groups. There's battery-to-battery communication within a group, and then each group communicates to its own inverter. So if Guardian is used, you use one Guardian per group. Each group must have the identical layout and quantity of battery modules and units. So if you have 4 eForces here, 1, 2, and 1, 2, you must have 4 eForces here as well. So 2 stacks. eWay 3 must have 2 eForces under it, and eWay 4 must have 2 eForces under it, if that's the case with eWay 1 and eWay 2. And each group must have almost at least identical PV input. What we are trying to avoid is that, let's say you're only charging with PV, and this has 5 kilowatts available, and this has 10 kilowatts available. So this group will get 10 kilowatts of DC power, this group will get 5 kilowatts of DC power. And on the other hand, the demand on the inverters is the same, because remember initially we said that on the AC side they're combined. So when the load is demanding power, both of the inverters give out the same amount of power. So what happens here is that they charge unevenly but charge evenly. So inevitably the battery group that was receiving less charge power will discharge faster, meaning you're going to lose part of your or partially lose your power output capacity, and you will lose part of your storage capacity. We want to avoid that. We want to have even charge and even discharge, and that's why we're saying each group must have at least almost identical PV input. Ideally, you go for identical PV input, but when the cloud flies over, maybe the PV strings that connect to inverter 1 are partially covered or something, that's fine. But in terms of the strings themselves on the paper, they ideally, as a target, they must be identical. Now, case 6, 2 times 3, using external bus bars. Many of you may be very familiar with this approach because, as I said, this is an age-old approach. It has been around forever, way longer than many battery companies nowadays. So, here you have it: inverter 1, eWay 1, and eWay 2. So eWay 1 connects to the bus bars, positive and negative. So eWay 1 right here. eWay 2 connects to, again, negative and positive bus bars right here. Note, the cable lengths of all of these must be identical. So on the diagram here, negative for the eWay 1 seems to be shorter, but in reality you would make it the same length as the negative for eWay 2, and again, same length you have for eWay 1 positive and eWay 2 positive. And then from the bus bar you have the connections to the inverter 1. So this inverter 1 has a shared set of battery bus bar or shared battery bank, and communication very simple: eWay 2 to eWay 1, eWay 1 to inverter 1. I know you might be thinking, oh, this doesn't make any sense. Initially, Geo said that you have 2 batteries, and there are even 2 methods of paralleling them with each other without the external bus bar. And same for 3, but again, I'm just laying out a concept in front of you. So for 3, this is what you would do. For 4, for 5, for 6, this would be the same principle, right? And I know that with 3, yes, you can use the internal bus bars. It just the slide is just this big. I cannot squeeze in 20 batteries in here. So if the principle here is clear for 2 or 3, I'm sure it will be clear for you for 5, 6, or 7 batteries or whatever have you. The communication, again, very simple: eWay 3 to eWay 2, eWay 2 to eWay 1, and eWay 1 to inverter 1. If you were to have multiple inverters, again, now this is the case where the internal bus bars would not be enough. Let's say you have inverter 1 and inverter 2. eWay 1 connects to the positive and negative, eWay 2 does the same thing, and eWay 3 does the same thing, and the inverters connect to the same bus bars. So essentially, these DC bus bars create a common pool of energy that the inverters can take power from or add power to, so that the batteries can charge. And the communication is as follows: eWay 3, eWay 2, eWay 1, and then from eWay 1 to inverter 1. Again, because this is a shared DC bus bar. It's not like the previous case when you had each inverter having its own group. But now that you know how it is for unshared battery banks, let's combine the unshared battery bank knowledge with the external busbar understanding and get to our bonus case, which I mentioned before, using external busbars and creating an unshared battery bank. This is what it looks like. So you have inverter 1, inverter 2. You have group of batteries for inverter 2. You have group of batteries for inverter 1. And it could be 5 batteries, 6, all the way up to 28, really, technically. That's how much we can cover with our communications, 28 batteries in one communication chain. So you see the groups are identical. You have same quantity of eWays. We presume that you have same amount of eForce stacks within the group as you have, same you would have for group 2 as in for group 1. And communication is for group 1, eWay 3 to eWay 2, eWay 2 to eWay 1, eWay 1 to inverter 1. For group 2 would be eWay 6 would communicate to eWay 5, eWay 5 communicates to eWay 4, eWay 4 communicates to inverter 2. So yeah, these are the principles, and I'm sure you saw the writing on the slide. Each busbar must have in capacity no less than 125% of the maximum continuous charge/discharge DC current that the inverters connected to it may deliver/extract. So you have inverter 1 here. It can deliver 250 amps, and so these busbars would need to be 250 multiplied by 1.25. How much would that be? God, I'm too tired. I'm not going to do that math now. So whatever that number is, that must be the smallest figure for you to have the busbars capacity rated at. And same applies for inverter 2. When we had the case with 2 inverters on one pair of busbars, 2 inverters, it's 500 amps. 500 amps multiplied by 1.25. Again, whatever it is, that's the number that you're going for, right? And yeah, these are really all the principles. Also, because we spoke about the eWays and Envy True12 so much, I will show you later maybe what the real unit interior looks like and how these 2 ports look like. So look forward to that, please. And for now, I do thank you for your attention. Thank you very much. See you next time.